Okay, I'll talk about multilingual NLP. And multilingual NLP is NLP in many different languages. There's specifically two varieties of multilingual NLP. The first one is monolingual NLP in multiple languages. And what I mean by this is basically any task that you could do in English, you could do it in languages that are not English. And so this would be question answering, sentiment analysis, chatbots, code generation, whatever else. And then the other one is some variety of cross-lingual NLP. And this is specifically tasks that handle more than one language at once. And so that would be things like machine translation, cross-lingual QA, et cetera, et cetera. Cross-lingual QA is just like, for example, answering questions where the source material is in a different language. So if I ask a question in Japanese, it can go find some information in English and answer the question in Japanese. So right now, so many of our systems are trained by, using large data sets. And probably by far the biggest challenge in multilingual NLP is this paucity of data in many of the languages that we care about. This particular example is of Wikipedia articles and how many Wikipedia articles there are in different languages. So you can see that it drops off very quickly. Number one is English, of course. And after the first 20 to 30 languages, there are just very few articles in any language that you want to use. It looks similar for just general text on the internet, but it's not quite as sharp in general text on the internet. So there is still this very long-tailed distribution, but it's not quite as bad as in Wikipedia. One other thing to note is that there's even less annotated data, of course, because the annotated data is a subset of monolingual data. And so that means we have less data for machine translation. We have less data for sequence labeling, dialogue, question answering, other stuff like that, instruction following and things. Another thing that makes multilingual NLP difficult is we just had a lecture on linguistics, and not all languages are the same. And I would say that this is the smaller problem, but it's still a problem. And it can cause issues when you're trying to process something that is not English with models that were mostly trained in English. And to give some examples, morphology is one of them. So we talked about how morphology, we can have things like, infix morphology, where you change the inner letters of a word. And in English, we mostly don't have that. We have like, goose, geese, and other things like this, but it's very rare for us to change the middle, to morphologically change the middle letters of a sentence, of a word. But in other languages, we have that all the time, and that breaks sentence piece, for example. So that's one issue. Another thing is accents and diacritics. So an accent or a diacritic is basically where you have another thing on top of the character to indicate its tone. Does anybody speak a language that uses lots of accents or diacritics? Yeah. Spanish. Okay. Yeah. So yeah, that's a good one. Any other ones? Yeah. Yeah, French has a little bit. There are some that are even more kind of rich, or to give one example, Yoruba, which is spoken widely in Nigeria, has lots of diacritics, but very often the language is written without them. So it adds a lot of ambiguity and like lexical diversity to the language and stuff like this as well. Pinyin kind of has them. So it has like Pinyin for Chinese kind of has them. It has like a number at the end of the syllable that indicates the tone. So it's kind of similar as well. Other things are different scripts, such as CJK, Chinese, Japanese, Korean scripts. So Chinese script is, they also use Roman characters, but they have lots of ideographs where the characters mean things, is supposed to be indicating the pronunciation. Japanese has both, both ideographs and regular characters that have pronunciations. Korean is all pronunciation, but they stick 3 pronunciations together in a single character. So like I don't know much Korean, but I maybe know enough to write this properly. So this is there a line down there? Does anyone know Korean? Yeah, is there a line? No, okay, cool. What?
The statement for the final one.
Oh, this is Korea, right? Yeah.
Then it has a line there.
Okay, okay.
Roundabout.
Yeah, so that's and then this is the yeah, okay. So this is Korea, Hanguk. Could you okay, thank you. And then this is yeah, so basically this is like H, A, N, and then kind of like K, KG, U, KG. And so like there's actually kind of 3 characters in each one of these characters. So it's kind of like an alphabet, but they're all stuck together. And if you deal with this on a computer and you're not very smart about it, basically it will just look like a Chinese character, and it will be segmented with sentence piece in a in weird ways if you use bytes or whatever. So each one has their own peculiarities. Another thing is dialectal language. So sometimes people speak different dialects, and that can throw things off. And also lack of formal writing systems. So for a lot of languages, there isn't really standardized writing, and people, sometimes write in the native script, sometimes write in Roman script, and other things like that. So English is relatively standardized, relatively poor morphology or simple morphology. Doesn't have a whole lot of characters and stuff like that. So it has a lot of simplifying things that you have to deal with when you work in other languages. So how do we start attacking multilingual problems? So like one really huge thing over the past 5 years or 7 years or so is that we can learn models that process multiple languages, and all the languages can learn from each other, and that really pulls up the languages that don't have a lot of data. And so this is a variety of transfer learning, and this allows you to improve accuracy on lower resource languages by leveraging data in higher resource languages. Another really big advantage of multilingual learning and learning models that work in multiple languages is practical, which is before Google Translate would deploy 100 models or maybe even 200 models, because if they were translating into English and then out of English, they would have one model for like English to Chinese, English to Japanese, English to French, English to Spanish, and then Spanish to English, French to English. And so they would have to deal with like deploying all of these models, having different servers that served all of them and stuff like this. Now you can just have one big model that handles all of the languages at once and deploy it, which allows you to make that model bigger itself because you need to deploy it fewer times. And also, it can benefit from transfer learning. So because of this, a lot of places that handle multilingual stuff are changing to this paradigm. In terms of like, let's say you want to handle a different language other than English, this is a high-level multilingual learning flowchart that you can kind of follow to decide which methodology you could be using. And this is from the point of view of wanting to get the best possible model. So first, is there sufficient labeled data in the target language? And when I say sufficient, obviously more is always better, but a reasonably large amount from the point of view of you being able to train a good system for the task you're interested in. For machine translation, that's something like at least 1 million sentences. For something like classification, it might only be 1,000 sentences or something like this. Then the second question is, must you serve many languages with strict memory constraints? If the answer is yes, you can do multilingual models. If the answer is no, you could still do a multilingual model, but you could also adapt to the specific language that you're interested in processing and do better by doing that adaptation. Then if you don't have sufficient labeled data in the target language, if you have access to people who can provide that data for you and you're serious about building a model for that language, you can just ask people to annotate things. So there's a lot of work on zero-shot adaptation, which is essentially trying to get models to work well on new languages with no annotated data. But in reality, like if you're ever going to be deploying a model to users, you might as well label 1,000 examples of whatever task you want to solve and train on those examples. And that's far easier than doing zero-shot adaptation. One caveat is if you're trying to show somebody like the possibility of something working. So like, for example, you have a nice speech recognition system that works in many different languages, and you want to show people in a new country that it could possibly work, then applying it zero shot and not using any training data might be a good way to convince them that they should work with you. But in the end, like if you care enough about it, you'll be annotating data. So this is my general like flow for building a usable system. Cool. Any questions so far? Okay. So let's go into multilingual language modeling. So multilingual language modeling, in the very simplest sense, is just like train a language model on lots of data. And so if you're just training like GPT or something like that, you just throw all of the data in there. You train your subword vocabularies over all of the data, and something will happen. You might want to do more than that, though, if you really care about performance. So anyway, if we're doing multilingual modeling, there's two varieties of multilingual modeling. The first one is if you have multilingual inputs. And if you have multilingual inputs, you really don't need to do anything in order to get it to work, at least somewhat, as long as your base model can handle multiple languages. So to give an example, like let's say I want to translate into English. If I want to translate into English, then I can just throw in these sentences and not say anything and say, please translate this into English. And GPT will do a reasonably good job of translating it into English for me. I don't even say this is a French sentence or this is a Japanese sentence or something like that. However, this may be very obvious, but like if you have multilingual output, at the very least, you need to tell it which language it should be generating in. So there's different ways to do this, but basically you can add a tag or prompt about the target language for generative tasks. And originally, this is what was done in Google Translate. It's probably what they're doing right now. And they basically added a single tag to the beginning that said French or Japanese, and then the sentence they wanted to translate, and then it gave them the output. However, there are a few difficulties in multilingual learning. So the first one is the curse of multilinguality. And so actually, if you look at a lot of the open source models, at least, most of them are only trained seriously on English. This includes things like Llama, Olmo, most of the language models that I talked about. And I think the reason why is this curse of multilinguality. And given a fixed size model, the per language capacity decreases as we increase the number of languages. And this is an older example from the XLMR paper, which was kind of a masked language model that was used in a bunch of different languages. But what you can see is as they increase the number of languages, the scores go down for the high resource languages as you get up to like 100 languages. For the low resource languages, the scores momentarily go up because you're now benefiting from transfer learning from other languages, but then they start to go down again as the model capacity runs out and you essentially do worse. And so this is an older paper. It shows it more convincingly, but There's also some other examples, like there was a very big effort by Hugging Face called Bloom, which was a model that was trained to be very multilingual, and they trained a 175 billion parameter model to try to make it, very strong in a lot of different languages, and it just ended up not being very good on English and being even worse on the other languages, because they kind of overreached their language, language modeling abilities at the time were just not good enough. I think things have gotten significantly better now, but still you'll notice that if you emphasize more on multilingual data, you do increase the number of tokens that you see in like English, for example, and that could cause accuracy to go down. Number of tokens and capacity available. Yeah.
So does that happen because we see transfer learning stop, or is it like another underlying reason?
Does it happen because we see transfer learning stop, or for another underlying reason? I think there's two reasons. The first reason is like if you have a fixed compute budget, then you're fundamentally going to be limited in the number of things that you can see. And actually, there's a nice paper by my student Patrick. I'm allowed to call it nice because it's not my paper, but I wasn't involved in it, but. I should have put this on the slides actually, but there's this this paper. Actually, maybe I did. But basically what they find is the amount of compute that you spend. Trying to find the main thing. So essentially the amount of weight that you spend on any particular sorry, I'd have to go back and take some time to look at the figures to explain them accurately. But one of the findings in this paper is the amount of time that you spend on any individual language kind of corresponds to how well you do on that language. And so if you're spending more time on one language, you do better on the other language. And there's the idea of scaling laws that I talked about before, where your effective capacity, or like how good the model becomes, is a function of like the parameter size and the amount of compute you spend. And if you're doing multiple languages, then you need to kind of, to some extent, split your parameters between languages. And one of the interesting findings from this paper is that actually you would expect more benefit from sharing than you actually get. Like you actually get relatively little benefit from sharing if you have enough data to train on. And because in many of the cases when we're training models, we're less bottlenecked by data for the low resource languages, or we're still bottlenecked by data for the low resource languages, but for high resource languages, we're usually bottlenecked by compute. So if you allocate more compute to other languages, then you're going to allocate less compute to English, for example. And a lot of people, like a lot of the benchmarks are in English for better or worse. So I think probably one good strategy here is, yes, we have some people focusing on building really good English models. We have some people focusing on building really good models for the top 10 languages where we can afford to build a model for each of them. And then we have some people working on, really good multilingual models that can handle a whole bunch of languages, and kind of just spread our efforts out and our compute for each of those models out over there. Yeah. Cool. Any other questions about this? Yeah.
Get what sharing means in this context. Is it a shared representation?
Yeah, so basically, usually what we do is we just train a single model, and all of the parameters are shared between all of the languages. The only things that are not shared are the word embeddings, and or the subword embeddings, and I'll talk about that in a little bit. Cool. So there's a number of ways to mitigate this curse of multilinguality. I kind of got ahead of myself in talking about the other paper, but there's a couple things that we can do to improve this. So the first one is the tokenization disparity, which I just talked about. The subword embeddings, we we share all of the parameters in the body of the model, but fundamentally the words in the different languages are different. Sometimes the scripts are even different. And so what we do is we usually have a shared tokenizer that's used between all of the different languages. And so if it's something like English and French with lots of shared words, then actually many of the embeddings will be shared between the different languages. That helps transfer, but it's not absolutely essential for transfer. So like there has been some work that demonstrates that even with no shared vocabulary, you can still benefit from transfer to some extent. But anyway, so with respect to the tokenization disparity, I tried tokenizing English in using the OpenAI GPT 3.5 and 4 tokenizer. And you can see that this content gave me 58 tokens. And then I tried to translate this into Burmese using Google Translate. I don't know Burmese myself, but I tried to translate it. And so this should be the same content, at least to the extent that Google Translate into Burmese is accurate. And then I got 617 tokens for the same content. And the reason why is because you can see here, basically, it's still got OpenAI, right? And interestingly, I didn't realize this. OpenAI isn't a single token in GPT's model. It's 2 tokens. But all of the other things are basically converted into byte level tokens. So each byte is a token. And because Burmese uses a different script, each one of these is like 3 bytes. So what you can see is it's a lot, more. So it's 10.6 times the total amount. And what does that mean? This means, number one, if you're processing Burmese with GPT-4, it's 10 times more expensive for the same content because they count by the number of tokens. Number two, because you're splitting it up into bytes like this, it's slow. Generation becomes 10 times slower because it generates tokens at a particular speed. And also it gets worse because the reason why we do subword tokens in the first place is because they kind of allow us to clump semantic units together. And if the semantic units aren't clumped together, the model has to use its capacity on combining together the tokens in the layers of the model, and that is prone to error. And it uses the model's capacity, and it does less well at modeling. So this is a pretty big problem for a number of reasons, cost, efficiency, accuracy. So one way to fix this, both from the point of view of training and learning tokenizers, is through heuristic sampling of data. And the most common way to do this is something called temperature sampling. And the way temperature sampling works is you essentially group the data into groups. And usually when we say groups, we talk about grouping into languages. And we sample the data according to its frequency, where we exponentiate the frequency by 1 divided by a temperature, and then renormalize, and then sample batches from each language according to that. So the probability of sampling a batch from language L becomes e to the frequency of L. Sorry. Frequency of L for the 1 divided by temperature normalized. So we have L prime frequency L prime 1 divided by temperature. And so what that does is essentially, if we have a data distribution from each language, which is kind of like a long tail distribution like this, normally you would sample this language a lot more. If you take the temperature and turn it into something like 5, that will flatten the distribution. So you'll sample the less frequent languages more and the more frequent languages less. And if you take a very large number, like 100, this will just flatten and say you sample like this from each language uniformly. And This sampling can be done both at model training time and at vocabulary construction time. And when you do it at vocabulary construction time, basically what that means is it will downsample English and upsample Burmese or any of the other low resource languages. So the low resource languages get more weight in creating the vocabulary, so they won't be split up as much like this. So I don't know if GPT does this, but XLMR does this, and Quen does this. So there are definitely language models that are attempting to be, more fair across different languages. Another thing that Quen does, I talked about this previously in the tour of large language models, but it also makes a much larger vocabulary. So normally Llama is like 32, and I think Quen was 32K, and Quen was like something like 215K or something. So they intentionally made the vocabulary larger so the distribution would be better across different languages. Yeah.
So how do you construct a batch for like machine translation? Like would a batch be assigned to English and French, and then another for English to another?
Yeah, that's a good question. You can do both. Sorry, just to repeat the question, how do you construct batches for like machine translation? Would you create a batch of English, French, or would you create a batch with like lots of different languages in it at once? I personally, what I would do, and I think what most people do, is they don't actually sample batches that are uniform in a particular language. And the reason why is because SGD, if you have lots of variance in your gradients, it makes it less stable. And so if you do all English French in a single batch at one time, that'll make it less stable because it will move all in the French direction than all in the German direction. So it's generally better practice to do this sort of upweighting or sampling before you form your batches. And another thing that you can do is you can do a bunch of this sampling at once, form a bunch of batches, and then run through all of them. And then when you get near the end, form some more batches and then throw them in there. So you can write data loaders to do that sort of stuff. Yeah. Cool. Nice. So there's also work on learning how to balance data. And this is a paper by my former student, Cindy. And it's kind of interesting. I don't know. I like it because it shows the possibility of what could be done with respect to things here. But it's a little bit expensive to run, so it might not be well suited for large scale pre-training, for example. But the basic idea is we have several training sets where the training sets are composed of different languages. And then we have several development sets, and these development sets are ones that we want to be good at processing, be it translation or QA or whatever else. And what we can do is we calculate gradients according to these various training sets. We also calculate the gradient on the dev set, and we calculate the alignment between the train gradient and the development gradient and see how closely they align. If they align very well, basically what it's saying is this training set is moving us in a good direction for optimizing the performance on the dev set. And if they don't align well, it's basically like harmful for optimizing performance on the dev set. And then we upweight or downweight the kind of mixing factor of these data sets according to how well the gradients align. And so why is this interesting conceptually? This is interesting conceptually because you can also do it as you continue training the model. And one of the problems with heuristic sampling is this number is very fiddly. And like this temperature number is very fiddly. It differs from data set to data set. And it doesn't fully give you the full spectrum of which data you should be upsampling. And this can allow you to learn it automatically. And just to give it an example of something it can learn that at the beginning of training, you should be maybe upweighting the low resource data sets, but then you start overfitting to the relatively small data you have for Burmese or relatively small data you have for some under-resourced languages. And so it starts actively like harming your model. And when it starts actively harming your model, then it will be automatically downweighted, so it stops harming your model, and then it'll be upweighted again when it makes sense to use it again. So this allows you to learn more nuanced strategies than this. In some papers, I think this was the Quen paper, but it might have been another multilingual large language modeling paper. They did something that was a little bit like this. No, sorry, it was the NLP paper that I'm going to talk about in a second. So they did something a little bit like this, which is that they started out training on higher resource languages and then gradually added in the lower resource languages later, because the lower resource languages have in some cases, have very little data, and you don't want to overfit to that data before the end of training when the model is capable of training on them. But again, that's just a heuristic, and there's probably better strategies, and hopefully doing something automatically would allow you to learn that. Cool. Any questions for that? Yeah, sure.
I guess going back to the one where you said the model had like 220K bootcamp size.
Yeah.
Do you not have the software issues and other issues that you have with the big bootcamp size replacement?
So 215K.
I guess opposed to 30K.
I mean, it definitely makes it slower. Yeah, for sure. The thing is, it only makes calculating the softmax and the word embedding slower. But if it makes the sequence length shorter, then you also benefit from a shorter sequence length, right? So it's kind of a trade-off. And I think, especially if you're processing lots of multilingual data, like 32K for English turning into 215K for 100 languages, it doesn't seem like a bad idea, right? Cool. Yeah. So then going to machine translation. Machine translation is like probably still the most important multilingual, inherently multilingual task that we handle. As we know, translation is basically translating from one language to another. And if we look at why it's difficult to translate, there's basically two reasons. The first reason is that there's syntactic divergences between languages. So we don't use the same syntax. So I put in this sentence, the development of artificial intelligence is a really big deal. And maybe everybody can, if you know another language, you can take a moment to think about how you would translate that into another language. And keep it in mind. And then I actually have Spanish, so hopefully I didn't mess it up because I have two actual Spanish speakers in here. My high school Spanish is that okay? Okay, good. Okay, thanks. What we can see here is that there's some divergence in syntax between English and Spanish. These ones are in the same order. The first divergence is that you use an article here in Spanish and you use no article in English. So it's not the artificial intelligence in English, it's just artificial intelligence. The second one is swapping the order of nouns and adjectives, which is a famous thing. Like actually English is the unusual language here. Most languages with similar word order to English put the adjectives after the nouns more often than they put them before the nouns. And then there's also a really big deal. I put in kind of like an idiomatic expression here, like big deal. And big deal won't be translated consistently into big and deal in other languages. So you can see that it turned into something else. Also, interestingly, this kind of went in the middle of big deal. So I also did it in Japanese, and Japanese has very different syntax from English. It's a subject, object, verb order language. So the verb comes at the end instead of the middle. And you can see that it's a little bit more crazy. Actually, this doesn't convey the full extent of how crazy the reorderings are between English and Japanese. It's just in a very, very different order. But you can see that actually in some cases it's more similar to English than Spanish is, because artificial intelligence is in the same order. So there are places where it's similar. Another reason why it's difficult to translate is lexical ambiguities. So this is an example from English and French, where different things in different words in different languages kind of are translated differently. So like a leg of a journey, a leg of an animal, a leg of a chair, and a leg of a human are all translated differently. And so I'm sure you can come up with other examples here. My favorite one is run, like run a marathon, run a program, run a company, a run in a stocking. Like all of these are different in most languages in the world. So this is really hard. There's also some other difficulties like that are language specific. Like in Japanese, they almost never say the who did something in conversational Japanese, for example. So if I say like tabeta, which means to eat, it could, or ate, it could mean I ate, you ate, he ate, she ate, the dog ate, you know. It ate, any of those things, and you don't know outside the context, and language models are pretty bad at, or translation systems are pretty bad at figuring out that context. So often in conversational translation, it should be like a question, like, did you eat? So like, tabeta, in that intonation means, did you eat? But it says, I ate instead, because that's the default, and it's really confusing. So there's all kinds of peculiarities like that as well. Translation tasks. There's WMT, which stands for the Conference on Machine Translation, which might seem a little bit strange to you because conference doesn't start with a W, but there are these shared tasks that are run every year for translation and evaluation. One interesting thing about this, which I might have mentioned briefly before, but I'll mention again, is here the translation systems and the evaluation systems co-evolve. So basically, every year they have a let's try to maximize translation accuracy task, and they have a let's try to maximize evaluation accuracy task. And always the evaluation accuracy task uses the systems from the translation accuracy task. And so every time they're trying to improve automatic evaluation on the like best systems of that year, which makes it really challenging to build good evaluation systems as the translation systems get better and better. So if you're interested in evaluation, I definitely take a look at this. It's a good gold standard for that. Another really good resource, which is not a shared task, it's called Flores. And it is a data set of 200 languages translated from English Wikipedia. And so it's data in lots of different languages. I like this for two reasons. The first reason is I believe Wikipedia is a really important domain to be able to translate because it has so much knowledge that's very useful. And if we could convey that knowledge to people in many different languages, it would be very beneficial to the people of the world. Another reason why I like this is because it's really hard to get high quality translations in 200 languages, just because it's hard to hire that many good translators and do quality control and stuff. And this was a data set created by Meta, and I definitely commend them for their ability in doing that. So this is kind of a standard for low resource language translation. And then IWSLT, there are tasks on speech translation. So if you're interested in speech, that's one you can take a look at. I'm not gonna, this isn't a class only on machine translation, so I'm only gonna go through it briefly, but there is one model that is worth taking a careful look at. It's the NLP translation model. And it's an example of building a strong MT model. It's open source, and they describe all of the stuff they do in doing it. And basically, to summarize, they start out with public bytext and a small seed of bilingual data and lots of monolingual data. They then train a multilingual embedding model, where the goal of the multilingual embedding model is to identify things that are good translations of each other. And then based on this, they run this multilingual embedding model over all the monolingual data that they have from multiple languages. And they try to extract mined bytext, where the mined bytext has a kind of confidence score of how good the mined data is. Oh yeah, and another thing that I forgot is language identification. Language identification is actually very hard. Trying to figure out which language something is written in especially once you start talking about 200 languages, they can be pretty similar. And especially, there's this amazing paper that I can show you. I don't have it in the slides, but it's Language ID in the Wild, Unexpected Challenges on the Path to a 1,000-Language Web Text Corpus. And just look at this figure in here. So here, the predicted language of this is Manipuri. I don't know why. It's clearly all emojis, but apparently the language ID system had to do that. Also, why you lion, why you always lion, and like all these little characters got predicted as twee. This is a misrendered PDF is of Varhadi, is Ayamara. This is a non-Unicode font. Yeah, more things like this. Creative use of Unicode. Meow is Pular. So there's just like lots of examples where, like actual web text can make language ID pretty hard. Fortunately, there are ways around this by having like very well curated training data for language ID systems and also having good confidence metrics for language ID systems, but it's definitely non-trivial. So after they did that, the language ID, they get this model. And in terms of modeling techniques, they use some interesting modeling techniques. The first one is mixture of experts. So mixture of experts is, I've already talked about it before in the context of the mixtural model. This and GPT models are also allegedly using a mixture of experts, but here it's particularly important because they're doing many different languages. And so if you're doing many different languages, you can use particular parameters for some languages and other parameters for other languages. So it's pretty helpful in that case. Another thing is curriculum learning. Like I just mentioned before, they start training on the lower resource languages later. Self-supervised training. So basically, the way this works is by having a denoising objective where they add noise to the monolingual data and then try to reproduce the original monolingual data. So they use that as well. Also, another important technique that is very widely used in machine translation now is something called back translation. And the way back translation works is like, let's say we want to translate in English to Swahili. English to Swahili translation model. And we don't have a lot of bytext for English and Swahili, but we have lots of Swahili. Basically, what we do is we train a Swahili to English model. And we generate a lot of like translated, like pseudo-translated English here, and then use that as parallel data. This is really widely used in machine translation. There is a caveat that this English is not natural, but that's actually kind of okay for a couple reasons. If the Swahili is actually natural, then at least the output is natural. So you're generating natural output, even if the input is a little bit unnatural. The other thing is actually as models get better, there's a lot of really bad translations online. Like for example, translations from not very good translators or translations from older versions of Google Translate, for example. A lot of the like data online is like old machine translation data. And so because of that, if you have a good back translation model, it might be actually better than your original data in the first place. So, so because of that, back translation can be pretty good. And they also incorporated the seed data that they created to seed the model. So this is a pretty good model. We did some evaluation of this from the language modeling perspective. And basically what we found was that it is quite effective. The NLP model is quite competitive, even with respect to the GPT models for lower resource languages under like the top 40. It's not as good for the top 40 languages. And if you compare Google Translate and ChatGPT on the top, kind of like the higher resource languages, actually GPT-4 can beat Google Translate on some languages like Romanian and other things like that. So, but anyway, the NLP model is quite good. So if you want to start out with a model, you can use this. There's also another more recent model called Seamless M4T that also allows you to do speech translation as well. And if you want to show your CMU pride, there's also Lego MT from Lei Li's group that you can use for this. Cool. Okay. I'd like to move on to multilingual pre-trained models. Are there any questions about what I talked about so far? Okay, cool. So I want to talk about multilingual pre-trained models. Closed LLMs such as GPT-4 are typically kind of like incidentally multilingual due to large training data. Open LLMs often do data filtering to allow for good performance on English, like I mentioned before. And so there aren't a whole lot of really good open options for standard left to right autoregressive models. I would say probably at the moment Quen is the best one, and I already covered that before in the previous class, so I'm not going to do it again. So, but what I would like to talk about is multilingual representation learning models and also encoder-decoder models, because they unlike in English, where I would say all the good models are autoregressive, the encoder, decoder, and mass language models are actually pretty competitive for multilingual tasks. So language model pre-training, such as BERT, has been shown to be effective, and it uses mass language modeling objectives. In models such as MBERT and XLM and XLMR extend BERT-style training for multilingual pre-training. Before I get into exactly how they do this, I'd like to talk a little bit about multilingual representation evaluation. And there's a few standard benchmarks that people use for kind of just general purpose skills of multilingual models. The first one is extreme, and the follow-up extreme R. And basically, the way they work is you have sentence classification, structured prediction, sentence retrieval, and question answering tasks across a pretty wide variety of typologically diverse languages, maybe something on the order of 40 different languages. Then there's also XGLUE, which is less typologically diverse, but also contains generation-style tasks. And yeah, extreme R is a harder version based on extreme. So the way that people do multilingual masked language modeling style objectives is unlike masked language modeling, where you mask out the input and you try to predict the output. What they can do is they feed in one sentence that's in one language, in another sentence that's in another language, ideally parallel sentences, and then mask things out. So the training code can be entirely the same or almost entirely the same, minus adding kind of language embeddings here. But they train the model so that it can kind of predict across the languages, which aligns the representations across languages better. And people have demonstrated that this is good for learning representations. Actually, in the there's also methods that can explicitly use alignments to improve the alignment between representations in different languages. But in the interest of time, I'll skip that and maybe get back to it if we have time. A very good model to know about, because I think this is still one of the best models for being used for multilingual processing, is MT5. And MT5 is based on the T5 architecture, which is basically an encoder-decoder architecture with a masked reconstruction objective. And the way that works, in case you know, we haven't talked about this in a while, so in case we need a refresher, the way it works is basically you have an encoder-decoder model that takes in an input, and you do like perturbations of the output. So you do things like dropping words, and you do things like dropping words from the output, reordering words from the output, and you try to get the model to reconstruct the original output. And so basically they train this on many different languages, and this gives pretty high performance overall for a lot of different tasks. And in particular, this model was trained explicitly to be multilingual, so it's it essentially has better performance at kind of like the long tail tasks than a lot of the standard language models that we have. There's also other versions like MT0 and byte T5. MT0 was instruction tuned further. Byte T5 was trained with no tokenization, just byte level modeling. And because it's byte level modeling, it allows it to model any script. You won't have troubles with Unicode and other stuff like that. I have personally found that MT5 performs better than byte T5, or at least it's easier to get it to work. So if you want a single one to start out with, I'd say MT5 is pretty good. But there's also other options. And I should also mention, actually, there was a fine-tuned version of MT5 recently, which was called so there was this model based on a large amount of kind of instruction tuning data. Trying to find their modeling page. Yeah, so it's based on MT5, but they trained it on a whole bunch of kind of instruction tuning data. So this is kind of like a more modern version of MT0, I guess. And I haven't played around with it myself a lot, but it's allegedly pretty good at instruction following and other stuff like this. Cool. I'd like to talk a little bit about some more advanced modeling strategies. And so for cross-lingual transfer learning, it leverages data from one or more high-resource source languages. Another thing that we often do is pre-training and fine-tuning. And pre-training and fine-tuning is good if you have a specific language that you want your model to be good at, because it allows you to specialize to that language. And as I mentioned, with the curse of multilinguality, it's hard to get a model that's really good at all the languages. There's also zero-shot transfer. And finally, something called annotation projection, or it's also called translate train in some literature. So pre-train and fine-tune, basically the way it works is you train on lots and lots of data from lots of different languages, and then you fine-tune on data in another language. And so this tends to work pretty well. It particularly works well if there was at least some data from the language that you want to train on in the original training data set. If there was no data from the language you want to train on in the original training data set, then it's pretty tough to get this to work because the model doesn't like already have knowledge of the language. Another thing that you can do is you can so one of the problems with adapting to low resource languages is obviously like lack of data, especially lack of supervised data. So another thing that you can do is you can train on that language itself and then a few other very highly related languages. And so if you know, like if you want to train for a particular, language from India or something like this, very often there's a few other languages from India, and sometimes some of them might be higher resource. So maybe like Hindi is related, and that's higher resource than the language that you're interested in training on. You can also do it, I mean, obviously you can do this for any language, for some languages, there's just no higher resource counterpart, which makes it a little bit tricky. But when there is, you can take advantage of that. This is also another example of something that, is a little bit tricky to implement because it requires meta learning and calculation of gradients and stuff like this. But there's this really nice work that essentially tries to learn a model that's good for fine tuning into different languages. And so the way they do this is, unlike standard multilingual learning, where you learn a model that is good at processing multiple languages and then try to fine tune it to a lower resource language, what you do is you try to learn a model that is good at adapting to low resource languages. And the way you do this is through a method called meta learning. I'm not going to cover meta learning given the limited amount of time. If you've heard about it before, you know basically what it is. If you haven't heard about it, just to give a general idea, what you do is you have a held out development set like I did for the data balancing thing. And you try to learn models so that the gradients that you derive from the updates here align well with the gradients on this data. And so you're trying to learn things where you update in a direction that is good for updating towards the low resource language when you start training on it. So these are all fine-tuning related things. There's a lot more to talk about with respect to this, like how do you choose languages and other things like this. Another big paradigm is zero-shot transfer for pre-trained representations. And the way that this works is you pre-train a large language model using monolingual data from many different languages. And then you fine-tune using annotated data in a given language like English. And then you test it on a model on a different language from the fine-tuned language, like French. And we benefit from this because multilingual pre-training can learn something, I shouldn't say a universal representation, but at least a representation that is conducive for transfer across languages. There's a lot of work on this. I am not going to cover it in a lot of detail, number one, in the interest of time, but also number two, because I do actually kind of strongly believe that there are other reasonable options that outperform this a pretty fair amount of the time. And one of them is something called annotation projection or translate train. And the way this works is very similar to what I talked about with back translation. But there's two varieties of annotation projection. The first one, translate train, is you have annotated training data in English, and you translate it to the language you want to process, like Swahili. And so this is relatively easy for like question answering or something like this. So what you do is you just take question answering data, you translate the question, you translate the answer, and now you have Swahili question answering data. And sure, there may be like translation errors or something like this, but having some training data is better than having no training data. And also, machine translation systems are reasonably good nowadays, so you can actually get reasonably high quality data. The more complex version of this is, what if you can't just translate your data? What if your translated data is not just text, but it's some sort of annotations on top of text? And to take the hardest possible example is something where you have like tags on every word. And so this could be like, for example, for part of speech tagging. And if you have part of speech tagging, what you can do is you can have English Swahili data. Maybe this is even, like already translated data. It's already translated data, but you have part of speech tags, either manual or automatic for the English data. And then you basically project the part of speech tags to the other language. And it doesn't have to be part of speech tags. It could be like named entity labels. It could be, any other variety of things like this. And this gets tricky because basically you need to find alignments between the words in the languages and then project the labels. And you need to think about things like, okay, well, if this is a noun, how do I turn it into two nouns? Do I treat this as a determiner? Like what sorts of rules do I use to solve these problems and stuff like that? So you can either just translate the data if you don't have these sorts of annotations, or if you have these annotations, you need to do some more tricky stuff, basically. Actually, I'm sorry, I forgot to talk about word alignment, and this is kind of important, so I'll just talk about this briefly. So word alignment, basically what it does is going back to the example here. Word alignment is basically getting these alignments between the individual words in the sentence. And so the input is a sentence in one language and a sentence in another language. And the output is like 0, 0, 1, 1, 2, 2, 3, 4, 4, 3, and kind of like the matching indices between the languages. And there's two ways to do this. One way is unsupervised. And unsupervised word alignment just uses co-occurrence statistics between different languages. And the most famous method for this, sorry, I should have a slide about this. I just realized now that I did not prepare a slide. So the kind of older version of this that was used forever is something called Giza++. It uses co-occurrence statistics over a large corpus to do annotation. A more modern version of this is something called Similine. And the way this works is you basically do multilingual BERT between these different languages, and you find the representations that are the most similar between the languages, and you treat those as alignment links between the words in the languages. And then there's also supervised alignment. In supervised alignment, you have a very small amount of data, and you try to train a model so that the alignment links match with the supervised ones. And this was created by us, but I do think it's the best option from the point of view of supervised alignment. And basically the way it works is you have a multilingual BERT model, and based on this, you try to find like which links match together, but it's also trained using a contrastive objective where you try to upweight the correct links and downweight the incorrect links on supervised data. So it tends to be quite a bit more accurate than the alternatives. Another option, if you want, is to ask GPT-4. And you could ask GPT-4 to do that, but it's expensive and not a whole lot better than using one of these like trained alignment tools. So I would suggest probably using this if you want to find alignments between words. And this can be useful for a lot of things. It can also be useful for visualization or a better understanding of like how cross-lingual models are working and stuff like that. So it comes in handy for a lot of different things. Cool. Any questions here? Yeah.
So just looking at the alignment, it seems to be pretty crazy for like English to Japanese, for instance.
Yeah.
Is there any work where you try to hop between languages? So like from Japanese to Spanish, then Spanish to
Where you try to pivot between languages. Yeah, so it's called pivoting. And there's a fair amount of work on this. There's a bunch of different ways you can pivot. You can pivot for word alignment, and pivoting is particularly useful when you have a low resource language that's very similar to a high resource language where you have lots of data. The other thing is like pivot translation is a thing. And so, for example, I don't know if Google does this anymore, but for a long time, Google would actually be translating through English to get into other languages. And it was all a black box, but you could tell they were doing it because you would suddenly get English words when you translate from Chinese to Arabic or something like this. And so like that's also done for translation and other multilingual tasks too. Another thing that I should mention is I talked about translate train. There's also translate test. So translate train, basically you translate your training data. In translate test, you translate at test time. So basically, like, let's say you want to answer questions that were posed in Japanese or something. You translate the Japanese questions into English and answer the question using an English QA system, and then translate the answer back into Japanese. And that's good to an extent. Like, it's usually better than a bad multilingual system, but worse than a good multilingual system if you put like a lot of effort into building a strong multilingual system. So. Although maybe for some of the really like difficult tasks like reasoning and stuff like that, it's better to reason in English. Like I talked about multilingual chain of thought reasoning. Cool. So yeah. Another thing is if you're transferring from another language, which language to use? As I mentioned, it should be a similar to the target language and a data-rich language. We actually have a study where we tried to figure out what variety of similarity is the best for transferring. So like, let's say you want to train a good language for, Thai. It's hard to come up with which language you should be using. One of the interesting things we found in this paper is we actually trained a model to try to predict which language would be the best to transfer from. But the most useful feature overall was how close the languages are on the globe, which is kind of weird, right? Just because languages are close on the globe doesn't mean they're similar. Like you could come up with Basque and Spanish, which are very, very different in every way. But languages that are close on the globe tend to be similar with respect to both vocabulary and syntax on average. And so because of that, it's a pretty good indicator that a language would be a good transfer language. If languages don't share the same script, actually, I have an example of pivoting here where we can pivot from Marathi into Hindi and then into another language for linking across entities. And so we demonstrated that you could pivot. Another thing that you can do, like as we mentioned in the last class, or Lindia mentioned in the last class, there's the idea of IPA, the International Phonetic Alphabet, which kind of gives you an idea of how things are pronounced. And in some cases, languages might have a different script, but if you normalize them into IPA, you could normalize them into the pronunciation, and actually things are pronounced rather similarly in a lot of related languages. One thing you need to be careful about, though, is we actually found this hurt accuracy in a lot of languages. To give an example, English and French. So if anybody has studied French, you know that if anybody has studied French as a second language speaker after studying English, you know that even though you can read the characters, you have no idea how they're pronounced if you're not a very good French speaker. And so basically, the way it's written is closer than the way it's pronounced. So you can't just normalize everything into pronunciation and just hope it works. So that's another technique that you use. I'd also like to talk a little bit about how we share parameters between languages. And there's a bunch of different ways we can do this. One is sharing all parameters. So just have a single model where all of the parameters are the same. Previously, there were methods that shared only like an encoder or an attention mechanism, also sharing some matrices of the transformer model, using a parameter generator to generate parameters per language. This is, I like this paper. It's one of my papers. I like this paper, but it's not super practical. But basically, we used a neural network to generate the parameters of the multilingual model. And we fed in things like information about what type of language it was and stuff like that. So kind of ambitious, but not, it requires a lot of parameters, so it's not super practical. But the more common thing that people are using now are things like language experts or adapters. And so the idea here about language experts is basically, it's a layer that you insert into a particular part of the, model. And this is a kind of adapter style parameter efficient training layer where you downweight and upweight, downsample and upsample. So it's kind of like LoRa or an adapter or something like that. So few parameters for the language. And then they also have a task-based adapter. So based on the task that you're solving, they add an adapter here. And they also demonstrated that you can pre-train models with language-specific parameters included in them, also from the point of view of an adapter. We have done a similar thing for summarization where we compared prefix tuning and LoRa. And we found that you could do a similar thing where you train a single model, but each language has its own prefix tuning parameters or own LoRa parameters. And that can be pretty effective at improving the capacity of the model. Yeah, I have very little time to cover the last slides, I guess. So I'll just very quickly mention what I was going to mention. So another thing you can do is create new data. One way you can create new data is just ask people to annotate data for you. But the problem is for low resource languages, it's often hard to get lots of data. So one thing we do is leverage something called active learning. The basic idea behind active learning is that you use labeled data. You do some training, you get a model. Then you apply that model to lots of unlabeled data and select some data that the model is highly uncertain about, and then throw that to annotation. And so basically what this does is this allows you to select data where the current model is not very confident or not very good or something like this. And this can be really helpful. It's not limited to multilingual learning, but it's specifically quite helpful in cases where you can annotate only a small amount of data. And so the basic idea is illustrated here for binary classification, where if you only annotate data randomly, you might end up getting data that doesn't tell you very well about the specific decision boundary. And as a result, a model trained on the few data points that you randomly select could be inaccurate. Whereas active learning kind of finds data directly on the decision boundary here, and that allows you to find more effective samples. There's two fundamental ideas, uncertainty and representativeness. And you want to come up with models, you want to come up with a data that selects data where the model is uncertain, but representative. And so actually you can select data only for representativeness, and it's relatively useful. So you can select only data that has lots of high frequency phrases, for example, for machine translation, and that will allow you to get better coverage of high frequency phrases. But uncertainty is also good because it helps you find like the model's current blind spots. The problem with only uncertainty is it gives you lots of garbage. It'll get, like, for example, for machine translation, it will select things with only emojis or something like that. And, that's not very useful to train your model. So I have more examples in the slides. I'm going to finish that up. But uncertainty, you can use model confidence. Representativeness, basically what you do is you try to get good coverage of the embedding space of all of the embeddings that you have for models. And you can also do this multilingually combined together with cross-lingual transfer. And we have some examples of how I have a few examples of how you can do that in the slides here. So